Einstein, when he was asked, where are we with the quantum, said this: "We all agree that the so-called quantum theory of today, although a useful device, is not a theory in the usual sense of the word, in any case not a theory that can be developed coherently at present. On the other hand, classical mechanics cannot be considered a generally useful scheme." So there you have it, Poincaré reluctantly accepting that the quantum really was inexorably part of the new physics that was coming into view, and Einstein recognizing that his insight into this quantum reality could not be integrated into a mechanics, not as a series of continuously changing laws that allowed you to describe deterministically exactly how things developed. This idea of the quantum of light was then taken up by Niels Bohr in 1912, a year after the Solvay conference. And Bohr's idea was as radical as it was simple to state. Namely, Bohr said maybe the orbits of electrons would not obey classical electrodynamics. Maybe they were located in what he called stationary states, that they simply orbited without, as classical electrodynamics would have it, radiating their energy away and eventually falling into the nucleus. Maybe they were just stuck there in these orbits, and that when an electron went down to a lower orbit, it changed its energy, and that energy would be emitted as a photon, one of Einstein's photon. The change of energy, call it delta E, would then be emitted by one of Einstein's photons, which had the energy Planck's constant h times frequency. This would explain why there were individual lines when you took a spectroscopic image, when you refracted light of, say, a burning flame, and looked at it, you saw in simple lines. For instance, in the hydrogen lines, they were discrete. It wasn't a continuous spectrum from blue to red. When Einstein heard about Bohr's ideas, he said, "Can it explain the spatial distribution of the lines in hydrogen, the so-called Balmer lines?" If so, Einstein continued, then Bohr's is one of the greatest discoveries. Bohr's idea was, in a sense, a matter of desperation. He had no explanation for why these orbits, these stationary states, stood the way they did. That was explained to a certain degree by de Broglie's thought experiment that if electrons were like waves, and waves could only constructively interfere if there were a whole number of oscillations in an orbit, that de Broglie could actually give an accounting of why the stationary states were the way they were, why only certain orbits were allowed. We can take a look at that in an analog system by looking at sound pumped around a tube and looking at the way the waves, when there's exact number of wavelengths, 2 or 3 or 4, in the tube, leads to constructive interference and a pattern of pressure that we can track by lighting flames on this tube. So we've been trying to understand the Bohr atom, and one of the most remarkable features of the Bohr atom is that only electrons of certain momenta can be found in the atom. That momenta are quantized, and therefore the energy is quantized for the different electrons. It can have one amount of energy, or 2 or 3 or 4, but it can't have 3.72. And in order to understand that, once the idea of an electron having a wave, a wavelength, and a wave structure was accepted, once de Broglie had proposed this, there was a way of grasping this. And that is that suppose you had an orbit, imagine this tube as being the orbit of a Bohr atom, then if, say, you had 2 wavelengths in the tube that fit in exactly, then that would be good because it would reinforce itself. And each time it would come around, it would hit, the peaks would hit peaks and the troughs would hit troughs. And that was good. But if you were to say a little bit more than 2, then the peak would be hitting troughs and the troughs would be hitting peaks. And as the wave went around, it would wipe itself out. So you wouldn't see any electron if it didn't have a wavelength that fit an integral number of times, 2 or 3 or 4 or 5 or 6 or 7, inside along the orbit. So this experiment, or this demonstration, is a kind of an analogy. It's a metaphor, but it's a working metaphor. And what we've got here is a tube, and we're going to pump propane into it and light up the flames all along holes on the top. And then by mounting a speaker in here, we can change its frequency. We can change the wavelength of sound waves going around through this pipe. If exactly 2 waves fit in this, then we'll see regions where the pressure is going up and down really quickly and we see a high flame, and places where it's being wiped out, where we'll see the flames practically disappear, and then a region of brighter flames or higher flames to follow. So what we're going to do is we'll start by lighting this up, and Wolfgang, if you could turn on the propane here, then light these guys up. The speaker is off right now, so we don't have any difference in the heights of the flames. Let me just come around. So now they're all lit, and we have an oscillator, which is going to make a sound, which you'll hear. And as that sound increases in frequency, as it goes to higher and higher tones, the wavelengths get shorter. So we're going to turn it up, make the frequency higher, until we get to exactly 2 wavelengths fitting around this. And when we do, what you'll see is there will be 4 peaks and 4 troughs. So you're beginning to see that, and here you go. We have 1 peak, then a trough, another peak, a trough, another peak, and a trough. So 1, 2, 3, 4 peaks. So there are 2 wavelengths of sound propagating through the propane in this tube. Now, Wolfgang, if you could turn the frequency up, what will happen is it starts to wipe itself out, because now the peaks are not hitting peaks and the troughs are not hitting troughs. But as we continue to increase the frequency, we'll get to the point where 3 wavelengths can fit inside the tube, and therefore 6 peaks and 6 troughs. Wolfgang's tuning the frequency to try to hit it exactly right. If it's a little more than 3 wavelengths, it doesn't work. If it's a little less than 3 wavelengths, it doesn't work. So we try to get it, and there we go. Now we have 1, 2, 3, 4, 5, 6 peaks and 6 troughs. So this corresponds to 3 wavelengths fitting inside this tube. That's what illustrates the Bohr atom with de Broglie wavelengths of electrons, that if we have an integral, a whole number of wavelengths that can fit around the Bohr orbit, then it reinforces itself. If it's not exactly right, it annihilates itself. And that's why, de Broglie said, we have the Bohr quantization of momenta and energy inside the atom. What happens in the old quantum theory is it becomes more and more elaborate as people develop new and more complicated ways of accounting for the orbits of ever more complex atoms. But none of this could get very far without radically attacking the fundamental principles of quantum reasoning. That happened in the period around 1925 to 27, in the creation not of a quantum theory, but of a radically new mechanics, quantum mechanics, to which we now turn.